Imagine you're updating a spreadsheet. If one cell is bad, the whole row and column must be wiped clean. Set matrix zeros is a pattern mastery 100 must-have, featured at Google, Meta, and Amazon to test your space optimization and matrix manipulation skills. Over 35% of candidates use extra space or miss subtle row/col edge cases. Master this and you'll be ready for any advanced in-place update problem. Let's break down set matrix zeros using the basic approach, so you can tackle any in-place grid update question with confidence. Given an MXN matrix, if an element is 0, set its entire row and column to 0, in place. 2D list matrix, of size MXN. The matrix is updated in place. Imagine handling a data table where any bad sensor reading, 0, wipes out all readings in that row and column for analysis. Interviewers might ask, how do you update a matrix based on its own data, without using a lot of extra memory? What's tricky? Naive. Use extra arrays to mark all rows/cols with 0 OM plus N space. Optimal. Reuse the first row and first column of the matrix itself for markers, O1 space. Must handle the special case of first row and column carefully, as they're both data and markers. First, scan the first row and column to check if they need to be zeroed at the end, save 2 flags. For each cell, I, J, if it's 0, mark its row and column by setting matrix I0 equals 0 and matrix 0J equals 0. On a second pass, use the markers to set cells to 0, skip the first row and column for now. Finally, zero out the first row/column if needed, using your flags. Let's clarify. Markers in the first row/col allow you to track zeros without extra space. The first row and column are handled last to avoid overwriting markers early. Edge cases. All zeros, full matrix zeroed. No zeros, matrix stays as is. Only first row/col have zeros. Use 2 flags, first row 0, first col 0. Scan the matrix for zeros, set markers in first row/col. In a second pass, for cells I, J, except first row/col, if matrix I0 equals 0 or matrix 0J equals 0, set matrix IJ equals 0. Zero out the first row/col if needed. 3 passes, 1 for flags/markers, 1 to update cells, 1 to update first row, col if needed. No extra arrays, just flags. The time complexity of this algorithm is OMN. We traverse the entire matrix a couple of times, where M is the number of rows and N is the number of columns. Now, let's look at the idea behind this solution. We are using extra sets to track which rows and columns should be zeroed. Here, M is the number of rows and N is the number of columns. The steps are, first, scan the matrix and record which rows and columns contain a 0. Then, go through the matrix again and set any cell to 0 if it's in a 0 row or column. Think of it like marking which rows and columns are infected with zeros, then spreading zeros across them. Store the number of rows in M and the number of columns in N. Create 2 sets to remember which rows and columns should be zeroed. Go through each cell in the matrix. If a cell is 0, add its row to 0 rows and its column to 0 cols. Go through the matrix again. If a cell is in a row or column that contains a 0, set it to 0. Otherwise, leave it as is. So, to summarize, this algorithm first records which rows and columns have zeros. Then it updates the matrix based on those records. It is simple, easy to follow, and effective. Extra space is used for the sets, giving OM plus N, space complexity. 2 passes over the matrix give OMN, time complexity. This approach is straightforward and easy to implement. We have a matrix where any 0 sets its entire row and column to 0. Input 111101111. The solution records which rows and columns have 0, then updates them. Output 1010001001. The function works correctly and efficiently. Worst case, the time complexity of this algorithm is OMN. We traverse the entire matrix multiple times, where M is the number of rows and N is the number of columns. Now, let's look at the idea behind this solution. We use the first row and first column of the matrix as markers to indicate which rows or columns should be zeroed. We handle the first row and first column separately to avoid overwriting the markers. Think of it like using the edges of the matrix as sticky notes to remember which rows and columns need zeros. Store the number of rows in M and columns in N. Create flags to check if the first row or first column contains any zeros. Check each cell in the first row. If a 0 is found, set first row 0 to true and stop checking. Check each cell in the first column. If a 0 is found, set first col 0 to true and stop checking. Go through the rest of the matrix, excluding the first row and first column. If a cell is 0, mark its row in the first column and its column in the first row. For each row, except the first, if the first cell is 0, set all cells in that row to 0. For each column, except the first, if the first cell is 0, set all cells in that column to 0. If the first row originally had a 0, set the entire first row to 0. If the first column originally had a 0, set the entire first column to 0. So, to summarize, this algorithm first checks and marks which rows and columns need zeros using the first row and column. Then it updates the rest of the matrix accordingly, and finally handles the first row and column separately. It is efficient, clever, and in place. No extra sets or arrays are used, so the space complexity is 01. We have a 3 times 4 matrix, 0 1 2 0 3 4 5 2 1 3 1 5. Every 0 sets its entire row and column to 0. The solution first records which rows and columns contain zeros, then updates the matrix accordingly. The output is 0 0 0 0 0 4 5 0 0 3 1 0. This confirms the function works correctly, efficiently updating all affected rows and columns. Breakdown recap. Conceptually, whenever a cell is 0, its entire row and column must be set to 0. The challenge is to do this in place without using extra memory beyond a few variables. Assess recap. A naive approach uses additional arrays to track which rows and columns need zeroing, but that costs extra space. The optimal approach cleverly reuses the first row and first column as markers while keeping track of whether they themselves need zeroing. This reduces space complexity to 01 while maintaining clarity and correctness. Structure recap. Here's the plan. Use 2 flags for the first row and first column to know if they need zeroing. Scan the matrix. For each 0 found, mark its row and column in the first row and first column. In a second pass, update the cells based on these markers, excluding the first row and column. Finally, zero out the first row and first column if the flags indicate it's needed. Implement recap. We implemented 3 passes, first to set markers and flags, second to update the inner matrix, and third to handle the first row and column. Running this on LeetCode executes cleanly and efficiently without extra arrays. Check recap. We verified that the solution handles all edge cases, including matrices with all zeros, no zeros, or zeros in the first row/column. Time complexity is OMN, and space complexity is 01. Closing insight. The key takeaway? By cleverly using the matrix itself as markers and handling the first row and column last, you can update the grid in place efficiently and elegantly. This approach generalizes well to many in-place matrix update problems in interviews.